In the previous chapter, we looked at a new reaction that alkenes could undergo, and we called this an addition reaction. And in an addition reaction, an alkene, which is a compound bearing a carbon-carbon double bond, remember that the double bond is actually composed of a fairly strong sigma bond plus a relatively weak pi bond. Okay, and then we would react that alkene with a reagent. I'm not going to worry about the nature of that reagent at the moment here, but the reaction would take place in such a way as the weaker pi bond of the alkene would be broken, and we would form two new sigma bonds. Okay, and those sigma bonds would be formed between the carbons of the alkene, or where the alkene was, and the different halves of the reagent that we reacted with. Now, one of the driving forces for this reaction to take place um, was the fact that part of this reagent that we were reacting with had to have at least a little bit of a positive charge somewhere, which of course means that it must have also had some kind of a small negative charge somewhere, which is what made it so attractive to the electron-rich alkene. Okay, so the alkene would be attracted to the positive charge on one part of that reagent. Now, we've seen this already uh, in the case of hydrohalogenation. And in hydrohalogenation, our reagent was either HBr, HCl, or HI. And again, we can see here that because of the nature of this being acidic, that H is going to have a little bit of positive charge, and then whatever the counter ion was will be negatively charged. Okay, what we're going to do here today in this video is we're going to look at a different type of addition reaction. It's going to have a lot of things in common with the hydrohalogenations that we talked about in the last video. For example, it's going to make use of Markovnikov's rule. It's going to have the same sort of stereochemical implications. Okay, so in the hydration of an alkene, again, we are starting off with a carbon-carbon double bond, and again, we'll try to keep this as general as possible. Okay, and this alkene is going to undergo reaction with a reagent similar to what we saw above, except it's going to be water. Okay, so you can see here I'm writing water a little bit weird as H and OH, but the purpose of that is to kind of align this with the diagram that I drew above. Okay, so in the course of this reaction, again, just like the hydrohalogenation, we're going to break the pi bond, and we are going to form two new sigma bonds. One of those sigma bonds is going to go to the hydrogen of water, and one of them is going to go to the hydroxy part of the water. So you can see that the overall effect of this reaction is that we are converting an alkene to an alcohol. Okay, so this is a very useful reaction. So synthetically, it's very useful. But we're going to take a little bit more time to talk about the properties of this reaction before we start using it synthetically. The first thing that we need to note here, first of all, is that the way that I've drawn this reaction, it does not actually proceed. In other words, in order for the reaction to work, I need to have something there to push the reaction along, something to speed it up, and we do that with the addition of acid. Okay, and probably one of the most common acids used for this would be sulfuric acid, mostly because it's very strong and because its conjugate base is not very nucleophilic. Okay, so here's how the reaction goes down. Okay, so the mechanism for this reaction okay, does not start off right away with having the alkene attack the H of water. Okay, the first thing that's going to happen is that the water is going to react with the sulfuric acid. Okay, so the first step will be the formation of the hydronium ion. Okay, so we get the formation of this intermediate. Okay, and then once we have that, now that is something that the alkene will be willing to attack. Okay, the alkene is not going to um, go through the trouble of breaking its pi bond just to try to attack this H that has very little positive charge on it from water. Okay, but now there's considerably more positive charge on the hydronium ion. Okay, which is going to pull electrons away from that H, which means the H will be much more positively charged. Okay, so then now that we have hydronium present, the alkene can undergo reaction. Okay, so the electron-rich alkene uses the electrons from its pi bond to attack the H of hydronium, and that's going to produce water as a byproduct. Okay, when that happens, we're going to break open the pi bond, and we're going to form a bond between carbon and hydrogen. Now, just like when we were talking about the hydrohalogenations, I'm not going to worry too much about which carbon gets the hydrogen because we really don't know what's on either side of these carbons. Okay, so in the course of doing that, we're going to generate a carbocation intermediate plus water. Now, at this stage, okay, we have a carbocation that's going to be hungry for electrons. So what's going to happen is it's going to react with the water that is produced as a byproduct, or the water that was just floating around anyway. Okay, so water comes in with its electrons, okay, and shares them with the carbon that's positively charged. Okay, and you can see here where we now form that carbon-oxygen bond. Okay, and the resulting intermediate is going to have a positive charge on that oxygen. And then the very last step here is for that intermediate to get deprotonated. Now, what's going to deprotonate it? Well, chances are it's going to be the most abundant base that's in the reaction mixture, and that's going to be water. Okay, so we can show water coming in and attacking that proton and giving the electrons back to the oxygen. Okay, and you can see here we wind up with our alcohol product. Oh, gave that thing an extra hydrogen there. Okay, and we regenerate the hydronium ion, which can then be used again for the next step of the reaction. So you can see here the the acid is catalytic. Okay, so this is how the reaction works. Okay, the things that you need to be paying very close attention to here are the fact that we have a carbocation intermediate. Okay, and what that means is that we have to look out for rearrangement. Remember that if a rearrangement can happen to produce a more stable carbocation, it will. Okay, the other thing that we need to look out for is because we have this carbocation rearrangement, that we are still bound by Markovnikov's rule. Okay. And in addition to that, one last thing, because we have this positively charged intermediate that is planar, that means that attack of the water in this case can happen on either face of that carbocation. So chances are we're going to see the formation of racemic mixtures whenever enantiomeric products can be produced. Okay, so let's look at a couple of examples here. Okay, so let's take a look at what happens when we use a non-symmetric alkene. Okay, and this is probably one of my favorite non-symmetric alkenes. You'll see this show up a lot in our conversations about addition reactions. This compound, let's say that we react that with water, okay, in the presence of an acid catalyst. Okay, I could have written just H plus there. I could have written H2SO4. Okay, either way, it kind of gets us to the same end product here. Now, how do we predict what the product's going to be? Well, remember, we have the two carbons that are part of the double bond. Okay, the pi bond between them is going to break. Okay, all the other stuff that was attached to them before the reaction will still be there. So these two methyl groups will be on the carbon on the left, and these two H's will be on the carbon on the right. Okay, now remember, the thing that we're adding across the double bond here is water, so H and OH. Okay, so just like we saw with hydrohalogenation, okay, there's going to be a preference for the hydrogen to go to one of these over the other. Okay, and again, we follow Markovnikov's rule. The H is going to go to the carbon that has the most hydrogens already, which is the carbon on the right. Okay, the OH is going to wind up being put on the most substituted carbon, which is the carbon on the left. Okay, so again, we have to abide by Markovnikov's rule. Okay, we call this the Markovnikov product. Incidentally, you can have an anti-Markovnikov product, and we'll talk about that a little bit more as we proceed. Okay, now I want to look at an example where the product that we form will be chiral. Okay, I want to use that same example that I used from hydrohalogenation because this is a pretty good one. Okay, where we have the six-membered ring with the two methyl groups, and then we have a double bond in the ring, and then we have a methyl group coming off the side there. Now, this time, instead of treating this with HCl or HBr, we're going to treat it with water. Okay, and again, with an acid catalyst. Okay, now I'm going to draw this out. Okay, so we have that six-membered ring, the two methyl groups coming off of it. Okay, we're going to form a bond between the carbon and the hydrogen because that is the carbon that has the most hydrogens on it already. So again, this carbon and this carbon is the same as this and this. Okay, we didn't draw it out, but there was already an H here. Okay, the one that was to the right of that did not have an H on it. So we can expect then that the OH will wind up here on the same carbon as the CH3. Okay, and this compound is in fact chiral. So there are two possible products. We can have the product that puts the hydroxy group coming out towards us, with the methyl group going away from us. Okay, or we can expect to see the opposite enantiomer, which has the the hydroxy group going away from us, and the methyl group coming out towards us. Okay, again, these are enantiomers, and because the intermediate that we go through is a planar intermediate, there's no preference for one attack over the other, and we wind up with a racemic mixture. Okay, and remember, that means that there's no optical activity. Okay, now a related reaction to the hydration is actually an alternative method for us to make ethers. Okay, so consider if we were to take an alkene. Okay, and again, we'll keep things general. But this time, instead of reacting it with HOH, so HOH being water, what if we reacted it with HOCH3, okay, which is methanol, an alcohol. Now, when I do this reaction, I'm not going to produce an alcohol like I did before when I used water, but what I will produce is an ether. Okay, so if I have an acid catalyst present, okay, what I can do is again break open that pi bond. Okay, form a bond between carbon and hydrogen. Okay, and this time we put an OCH3, okay, which is an ether. And this reaction works for all alcohols. Well, I mean, I'm sure there's some exceptions, but for our purposes, we can use this for any alcohol. Okay, and the way this works is exactly the same way as what we saw with the hydration reaction. Okay, the only real difference here is what's attacking once we have the carbocation form. Okay, so just as before, we start off by protonating the alcohol. Okay, so notice in this case I haven't drawn out the rest of the acid. I just kind of left the H plus there, and that's perfectly acceptable. Of course it is I'm the one who's doing it, and I'm the one who's grading, so. But if you look in journals and things like that, you'll see this all the time. Okay, so we make what kind of looks like a hydronium ion. It's not really a hydronium ion, but it behaves a whole lot like it. Okay, so that the alkene can come in with its electron-rich pi bond and steal a proton, okay, from here. Okay, notice that at this point we break open the pi bond. We form the carbon-hydrogen bond, and we generate a carbocation intermediate. And just like before, it's a carbocation. That means that we are still going to have to worry about Markovnikov's rule. We still have to worry about stereochemistry producing enantiomers. And of course, the biggest thing, we have to worry about rearrangement of that carbocation if it can rearrange. Okay, and then we regenerate. Make sure I'm consistent in how I draw this. We regenerate the alcohol. Okay, then we can see the carbocation reacting with the lone pair of electrons on the methanol. Okay, so they come in, and we form a bond between the carbon and the oxygen. Nope, not that oxygen, not there. Hold on. Okay. Okay, and look what's still attached to this oxygen. We still have an H here, and we have a CH3. Okay, we have a positive charge on that oxygen, and at this point we are primed for something to come in and remove that proton. Now, again, the most likely base is going to be the base that's most plentiful and is still strong enough to remove that proton. And some of the methanol that we had in the reaction should be more than strong enough to do that. Okay, so the electrons come in from the methanol, attack the H, and push the electrons back onto the oxygen. Okay, which brings us to our product, which, like I said earlier, is going to be an ether. In this case, it's a methyl ether. Okay, and then we regenerate that kind of hydronium analog of the alcohol, which can then undergo the next step of the reaction and proceed through. And still, we see that the acid is catalytic in this particular reaction. Okay, and again, you still have to look out for all the other pitfalls that come along with carbocations.